hi all, this is Dr. K. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process. The topic is Ion Beam Machining Problems and Solutions. Right. At the end of this session, student will be able to solve the problems on material removal rate of ion beam machining. Of course, if in the given data material removal rate is given, some other parameter or value may be required to find. So students can be able to find those values. Okay, right. So before we discuss the problems, now let us look at the non-traditional machining processes. Okay, so now we are discussing ion beam machining. Okay, problems and solutions. But however, let us discuss non-traditional machining processes for the better understanding. So here, non-traditional machining processes are classified into mechanical, thermal, chemical and electrochemical. Okay, so in mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ion jet machining. Okay, in thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining and plasma beam machining. Okay, right. In chemical and electrochemical, chemical machining, photochemical machining and electrochemical machining. Right now we are in this, okay, ion beam machining problems and solutions. Right. Now let us discuss problem number 1. Material removal rate calculation. So usually we need to find the material removal rates. Okay. Of course, if some other data is given, we need to find the respective or required values. Okay. Right. Problem number 1. An ion beam with a current of 5 milliamperes and ion energy of 10 keV. Okay. Electron volts here. EV means electron volts. Is used to machine a silicon wafer. Okay. If the sputter yield is 2 atoms per ion, calculate the material removal rate in atoms per second. Okay. So here what is the given data? Ion current, okay, 5 milliamperes. That is given. We have to convert into amperes. Okay. So 5 into 10 power minus 3. Okay. Next, ion energy 10 kilo electron volts. Okay. So that is given keV, electron volts. Okay. Ion energy. Next, sputter yield is 2 atoms per second. So that is also given. Okay. Now, number of ions per second. Okay. That is 1 by Q, where Q equal to 1.6 into 10 power minus 19 C. Okay. So this is a constant. Okay. We have to assume. Number of ions per second can be calculated now. Okay. So here, number of ions per second equal to 1 by Q, where Q equal to this one. Okay. Now we have to find number of ions per second. Only Q value is given here. So we have to, that is 1 by Q. Okay. 1 by Q means this value will come down. Okay. Right. But here, ion current is given na I. This is not 1 by Q, 1 into I by Q. Okay. So I value is this one. And Q value is this one. Substitute the values. Okay. So number of ions per second equal to I by Q, where Q is the constant. Okay. So I value is given. Okay. Now MRR equal to number of ions per second into Y. Okay. What is Y? Sputter yield. Okay, sputter yield Y. Okay, so multiply with that so that we get MRR, material removal rate. Right, here the thing is that where do we use this ion energy? Have we used that one? You check once. Have we used or not? Here 5 into 10 power minus 3 by this one Q value. We have not used this ion energy. Okay, so that is superfluous data here. Okay, sometimes the data may not be useful to calculate the material removal rate or something. Okay, and usually we feel that that ion energy is given, so from that we may get something like that we think, but only the matter is that we have to focus on the concept and the relevant parameters. Then only we will be able to solve the problem appropriately. Okay, so students should understand some superfluous data would be there in the problem. Okay, that's what I want to reiterate. Right, next second problem, depth of cut calculation. Okay, right, a 5 keV ion beam is, so that is nothing but energy. Okay, right, ion energy is given. Okay, 5 keV. Okay, first let me read the problem. Okay, we use it to etch a copper surface. The surface yield is 3 atoms per ion. If the beam is applied for 10 minutes over an area of 1 centimeter square, calculate the depth of cut. Assuming the density of copper is 8.96 grams per cubic centimeters and atomic weight is 63.5 gram per mole. Okay, so now let us see what is the given data and how that we can find the depth of cut. Okay, right, ion energy is given. Okay, over. Next, sputter yield 3 atoms per second. Okay, given. Next, time is given. Okay, beam time, that is 10 minutes. Okay, we have to convert into seconds. Right. Next, area is given 1 centimeter square. Okay, now we have formula, number of ions per second. Okay, number of ions per second, that is I by Q. Q is the constant, I is the current in amperes. Okay, right, assume ion current I equal to 1 milliamperes. Okay, here the current is not given, so we have to assume. Okay, and number of ions equal to 1.875 to 10 power 19 ions. Okay, so 1.875 into 10 power 19 ions. Okay, right. Now number of atoms sputtered. Okay, that is 1.875 to 10 power 19 into 3. Okay, why? Here sputter yield Y equal to 3 atoms per ion. Okay, so 3 is given here, so multiply with that 3, so that we will get the number of atoms sputtered. Okay, right. So here this value we have to assume, and here sputter yield Y equal to 3 atoms per ion. So number of atoms are this many. So 3 atoms per ion means we have to multiply with this 3. Okay, that's what we have did here. Next, convert atoms to moles. Okay, so moles equal to same 5.625. This is the old standard one. 5.625 625 into 10 power minus 19. So this value, number of atoms per sputtered, by 6.022 into 10 power 23. Okay. So this is standard, already we have studied in our earlier studies. Okay. So that value is 9.34 into 10 power minus 5 mole. Now mass removed equal to this moles, that means 9.34 into 10 power minus 5 into 63.5. Okay. So here number of ions, from that number of ions we got number of atoms sputtered. Okay, from that we are converting into atoms to moles. Okay, so while we are converting into moles, this standard numerical that we have to use 6.022 into 10 power 23. Okay, so that we will get in mole. Okay, so once if we get that value, we have to multiply with this standard 63.5. So approximately that value is 5.94 into 10 power minus 3 grams. Okay, now what is the volume removed? So is area given? Look at here, 8.96. Volume removed equal to 5.94 into 10 power minus 3 by 8.96. Okay, so here also this one area. Okay, have we find that area? Yes, 1 centimeter square is given, but here is 8.96. Okay, approximately that is 6.63 into 10 power minus 3 cubic centimeters. Okay, so depth equal to 6.63, okay, into 10 power 4 by 1. So finally this value is 6.63 into 10 power minus 4 centimeters. Okay, right. Now problem number 3, energy deposition calculation. Calculate the total energy deposited on a material surface by an ion beam of 1 milliamperes and ion energy of 15 keV over a duration of 5 minutes. Okay. Now ion current I is given. Okay. Right. Ion energy is given. Okay. Next, time t is given. Okay, and see, let us see ion current how much, 1 milliampere, so we have to convert into amperes. Next, ion energy, so that is 15 keV. Okay, so 15 into 10 power 3 into 1.6 into 10 power minus 19 joules. Okay, we have to multiply with this standard. Okay, right, that is Q. Right. Time t 5 minutes, so we have to convert into seconds. Now number of ions per second equal to I by Q. So what is I? This one, and this value is Q, so that we get 6.25 into 10 power 15 ions per second. Now total ions equal to 6.25 into 10 power 15 into this 3 seconds. Why? Because this much time has released, so that it will be equal to 1.875 into 10 power 18 ions. Okay, so total energy deposited equal to 1.875 into 10 power 18 into this energy 15 keV, so 15 into 10 power 3, again this value. Okay, 1.6 into 10 power minus 19. So finally this value is 45 joules. Next, beam spot size calculation. Okay. If an ion beam has a divergence angle of 0.1 radians and is focused on a workpiece located 50 centimeters away from the ion source, calculate the beam spot size on the workpiece. Okay. So here radians is given. Okay. Divergence angle. Okay. 0.1 radians. Okay. Next, distance. It has located at a distance of 50 centimeters. Now, beam spot size D equal to, we have formula 2 times D into tan theta by 2. Okay. So, beam spot size equal to 2 into D is given 50 centimeters into tan of theta by 2. Theta is 0.1 radians. So, finally, we get 5 centimeters. Okay. Next, ion flux calculation. Fifth problem. A substrate is exposed to an ion flux of 1 into 10 power 18 ions per centimeter square per 2 minutes. Calculate the total number of ions that impact a centimeter square area of this substrate during this time. Okay. Right. What is the given data? So, ion flux phi is given. Okay. That is 1 into 10 power 18 ions per centimeter square. And time t 2 minutes is given. Okay. And total number of ions n equal to phi into area into time. So, substitute the values so that we get this value. Okay. Right. Problem number 6. If a 10 keV ion beam with a current of 2 milliamperes is used to sputter a material with a sputter yield of 4 atoms per ion, and beam is applied for 30 minutes. Okay. Calculate the total volume of material sputtered if the density of the material is 7.5 grams per cubic centimeter and atomic weight is 50 gram per mole. Okay. So, here the given data, I is given 2 milliamperes, convert into amperes. So, multiply with 10 power minus 3, and sputter yield Y is given, okay, 4 atoms per second. So, that one. And time t 30 minutes is given. Okay, convert into seconds, 30 into 60. So, 1800 seconds. And material density 7.5 gram per centimeter cube. And the atomic weight is 50 gram per mole. Okay, right. Now, as usual, okay, number of ions equal to, okay, so this is the standard. Okay, so here this value is I. Okay, so that finally this one is time. Okay, so finally we get these many ions. Okay, number of atoms sputtered equal to this one. Okay, so we get this value. Okay, now convert atoms to moles. Okay, this is the standard already we have discussed. Okay, so that we will get in moles. Okay, so finally we get in grams. Okay, so mass removed equal to, see here, atomic weight 50 grams per mole is given. So multiply with this 50. This value is given. Okay, so volume removed equal to this 0.75 by 7.5. Okay, so material density is 7.5. So divided with this 7.5, so that finally we get 0.1 cubic centimeters. Okay, so with this, this is the reference. Okay, thank you very much. With this this presentation.
Like, share and subscribe. Hit the bell icon for more updates.